exponent.
Yes, one second. I'm just copying the problem down.
All right, that's good because I need time to get my integration tool up as well. Which there.
Okay.
Yeah, your mode should be in radian. If it's not, you might get something you don't expect.
What did you just say? Can you repeat?
Yeah, the mode on your calculator should be in radian.
Yeah.
Which is kind of implied here, but easy to.
I got 153.
Yes, 154 for this one, rounded up. So 154 fish entering the lake. Any questions on that before we move on to part 2, part B?
No.
Okay. All right. What is the average number of fish that leave the lake? One word makes all the difference. You leave the lake per hour over the 5-hour period from midnight to 5 a.m. So this is the average value integral. It's the integral from a to b, 1 over b minus a, L of t dt. So for you, this is 1 over 5 minus 0, 0 to 5. Your L of t is a different function altogether, 4 plus 2 to the 0.1 t squared. Another thing you'll notice is that this is an impossible, you don't know how to do this integral. I'm not even sure if it has a known integration, so you have to use your calculator for this. There's no other way.
Okay.
So another integral, I'll do the same, work it out here.
I got 6.01.
Okay. I'm in the same ballpark here. I get 6.1. It doesn't say what to round to, so not really sure what you're supposed to say, but it's fish per hour is the units here. So it's all about interpreting the words and saying, okay, this word means this calculus thing that I've learned over the year. All right. All right. At what time from 0 to 8 is the greatest number of fish in the lake? All right. So we're not given the number of fish. We're given the derivative. We're given the derivatives of how many enter and how many leave. So if we were to look at some sort of a graph of this, okay, and remember that we're looking at derivatives. This is like y prime here and t from 0 to 8. Do you remember what sort of a crossing gives you a max or a min for the original?
What do you
Whether
mean?
So let's go back and look at something like this. If we know it's y equals x squared, and we look at a graph of its derivative, which we know is 2x, but you can see that it's decreasing and then increasing. How does this point up here at the bottom of the vertex correspond to this point here? Like, what do we infer from it? Imagine we were only given this. How could we know that it's a min?
Because the slope.
The slope changes. The slope changes from being negative to positive. So this down here is the slope of the derivative.
Mm-hmm.
And the derivative changes from being negative to now positive, below the x-axis to above the x-axis. Notice that this is decreasing. This is increasing. So a min, the whole point is that a min occurs when you go from decreasing to increasing.
Okay.
And a max occurs when you're going the other direction, from increasing to decreasing. So what I was trying to get you to think about is this graph down here, and then the other one, which is, well, what happens if it's going the other direction? That's what we're looking for. We want to know where the derivative goes from increasing to decreasing.
Mm-hmm.
So what we're looking for here is something where the graph crosses. Okay, so to do that, we really need to graph E of t minus L of t. So we want to get a graph of this. So we're gonna, and there's really no other way to do this. So E of t is the 20 plus 15 sine pi t over 6 minus 4 plus 2.1 t squared. So we want to graph that. If you want, I could do it on T83. I typically do my graphing on Desmos just because it's easier to visualize, see all the features. But I'm happy to do it on the TI if needed.
Mm-hmm. Wait.
If you're not sure what I'm talking about, let me know. I can try to clarify.
Wait, yeah, can you clarify?
You've got a graph. You need to graph this. And I'm asking you, I'm saying, like, do you need help graphing this in your calculator?
But when you graph it, like, what do you look for?
A crossing. Somewhere where it goes from positive to negative.
Okay, wait.
How are you doing on that?
Wait, I'm trying to see. One, two. trying to figure out how to get the. Wait, so once you get the graph, where do you press to figure out the zero?
So if you're doing on T83, it's a second calc, and then there's an option for 0.
Yeah, I
And it,
did that. And then it says like,
so you have to, it's going to say left bound. So you have to choose something left of it. And then it'll say right bound and you choose something right of it. And then you always guess in the same place you just checked out.
and then for what do you press for guess?
The same place you just did for right bound.
Oh, okay. So I got 6.2.
Yes. So your graph right there, whatever that is, 6.2. Now we need some units. We can't just leave it as 6.2. So that's all in the context of the problem here. So it says at what time. So it's hours since midnight. So it's 6 a.m. plus whatever 0.2 is. So you have to take 0.2 and multiply it by 60 to get the minutes. You know, I don't know how precise they want you to be, but you know, you want to at least say, okay, well, 0.2 times 60, 6:12 a.m. Because our time is not base 10, unfortunately.
Okay, so okay.
All right, D. All right, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? Okay, so they're asking about the sign of the derivative. The sign of the derivative at t equals 5. Okay, so if you recall from the original functions, they're the rates. The original things they're giving you are rates. So they're really just asking you to evaluate E of 5 minus L of 5. That's it. They're not asking you for anything more complicated than that. And this is an example of a problem where if you're stuck on like part C or B, they're all kind of independent. So you can actually do any of the parts without the previous answer in a lot of cases. So this one's just literally asking you to evaluate E of 5 and L of 5.
Mm.
Just be careful with your signs. When you're subtracting, you're subtracting the whole function.
Wouldn't it be for rate? Wouldn't it be the derivative of E?
The problem says fish enter a lake at a rate. They're already
Oh, okay. So that already is a derivative.
yes, and that's where these problems get to be unclear, because you think, oh, maybe I got to take a derivative of that. No, if they give you a rate, the rate is the derivative.
I got 17.84.
I got a slightly different result here. Guessing maybe just a sign error. Wait, hang on. Maybe I made the mistake. It's not going into the denominator. All right. That's 0.1 times that. All right. Sorry for the delay. I'm using a different calculator than usual. Takes a little longer. Yes, you got it. So it is 17.8. So it is increasing. Notice you don't have to say how much it is. You just have to say increasing or decreasing. You do have to show your work though. I don't think you can just write increasing. You gotta say something like greater than 0 or give the value. Either would be good. All right. Any other things to say, think about for number 1? Okay. Number 2, you're always going to get a problem on the AP with some sort of a table. Yet again, they're giving you a rate. That's the rate is the derivative. There's some sort of context here. Typically, you get some sort of integration whenever you have a table like this. So be on the lookout for that. All right, velocity of a particle P moving along the x-axis is given by the differentiable function Vp, where Vp of t is measured in meters per hour, that's the units, and t is measured in hours. Selected values of Vp of t are shown in the table above. Particle P is at the origin at time t equals 0. So that part of it's good for like integration probably, or asking where the particle is at. Now it says justify why there must be at least one time t for 0.3 to 2.8 at which v prime of t equals 0 meters per second. So you're basically looking at these 3 points here. If you make a quick sketch, 55 minus 29 and 2.8, we have some sort of thing that's going down and coming back up. So how do we know that the acceleration must be 0 for something like this that's graphed here?
The slope equals 0.
Yes, there's a horizontal tangent somewhere. Now, to be more specific, we're supposed to use the fact that, do you see how these are the same?
What are you saying?
The y, do you see how these values are the same? The y values of the velocity are the same.
Yes.
So what that means is they started and stopped at the same height. So there must be at least one place where, like you said, the horizontal tangent is 0. This is, and you'll see this on there, you're either going to get a Rolle's theorem or a mean value theorem on there, not the DMV, but MVT. Let me quickly, have we talked about this before? Rolle's theorem, mean value theorem.
I think so, but you might want to go over it again.
Sure. Yeah. Yeah. That's why I'm trying to figure out how far back we've got to go. The Rolle's theorem is used in this scenario where their heights are the same. So somehow you might want to remember that they're looking for maybe something as simple as saying that there's a sign change in the derivative between the 2 points. I mean, indicating there's a horizontal tangent, to the more full, Rolle's theorem explanation. And let me snip that in here so you can see that. I don't really know. I'd have to look at the way they grade this to tell you for sure. But the Rolle's theorem, they're looking for it's continuous. So you would say something like it's continuous from 0.3 to 2.8. And then you'd say it's differentiable from 0.3 to 2.8. The more important one is that the two endpoints equal the same value. The mean value theorem is the more generalized one, which is also in play. The mean value theorem, just kind of as a side here, the way it works is between 2 points. There's a slope there, and then the curve will also have a slope at some place that's parallel to that. So you got to give some of that information here. And it depends how formal you want to be. Either just say, yeah, the derivative changes sign somewhere in the interval, or you say full on, Rolle's theorem, continuous, differentiable, and the endpoints are equal.
Okay.
Is that sufficient for part A?
So what do I write?
I'm not sure because I don't know how much detail you need to give. You either can say there's a sign change on the derivative between the 2 points because it clearly goes down and then it goes back up. Or you say the function is continuous from 0.3 to 2.8. It's differentiable from 0.3 to 2.8. And f of 0.3 equals f of 2.8. We'd have to look at the rubric to know what they were looking for.
Okay. Okay. So I wrote it down.
Okay. All right, so problem B. For some reason, I wish I knew the answer to some of these questions, but they always emphasize trapezoidal rule. Why trapezoidal rule? Don't know. But they're saying use the trapezoid rule with 3 subintervals like these: 0 to 0.3, 0.3 to 1.7, 1.7 to 2.8. The thing that maybe makes this different than what you saw in class is that probably when you did trapezoidal rule, the widths were always the same. You don't have that here. You've got to literally look at it like 3 trapezoids: this trapezoid, and then this trapezoid. And it's kind of a pain to do it that way, but that's the way you got it. So if you recall, the area of a trapezoid is the width, obviously, but you have base 1 and base 2, and you've got to find the average of those. Okay, so it's not like because your formula for, you probably had a formula for trapezoid rule where it was like f of a plus 2 times f of a plus delta h, and then keep going, 2 times f of a plus 2 delta h. While that's true, it doesn't work. It doesn't really help you here. You have to make the physical shapes. Okay, so the way to do this is to look at these 2 points. Think of this one down here is 0, or this is 0.3 height. I'm sorry, 0, 0 height. Sorry, I'm all mixed up here. For the first one, the height is 0, 0. And then you got this other point up here, 0.3 comma 55. Okay, so this one isn't really drawn to scale. It actually really looks more like this. It's more like a triangle, but you should still treat it like a trapezoid. So the short of it is you have to take the average of the outputs, and then you multiply by the width, the delta x, which is the right minus left. So that's for the first one there. So for the next one, the y values are the bases, so it's the average of those. times the width, 1.7 minus 0.3. And then you do the same thing for the last one here. So it's half 55 minus 29 times the 2.8 minus the 1.7. Then we got to calculate this. Or I think you can leave it. There might be a good thing to double check with the rubric if you can just leave it and give the answer in terms of its units, which is the meters. Or we can calculate it out. It's up to you.
Why I'm still copying it down. Did you get 40.75?
I did not calculate it. If do you need the correct answer, or you just want to double check your answer? Like, are you graded on whether it's right or wrong, or what's the?
No.
Yeah, you can. I mean, it's up to you if you want to calculate, but it's meters or distance in this problem. Fill in the blank there. The setup's the important part. Knowing how to do the trapezoid rule, remembering the formula. They don't give you the formula for that, and it can be. It's tough. You got to know how to substitute the numbers and which one's the height, which one's the width. The width is always the change in x or change in t in this case. All right. Second particle Q moves along the x-axis, so its velocity for 0 less than or equal to t less than or equal to 4 is given by vq of t equals 45, square root of t cosine of this thing. So again, notice like this is not simple. You're not going to do this by hand. You're going to have to use the calculator. Find the time interval during which the velocity of particle Q is at least 60 meters per second. Okay. Or I'm sorry, meters per hour. So that's the first, that's like part A of this, part I. Then find the distance traveled by Q during the interval when the velocity is at least 60 meters per hour. So they're giving you the velocity function. They're telling you, they really want to know when V of Q is greater than or equal to, say at least 60. Okay, so what you're looking for is on some interval from 0 to 4 here. Where is this function? I have no idea what it looks like, but it's like, where is it above, where is it above 60? So this is probably a graphing exercise. I'm going to do that myself here and see if it works out. They never give you something simple to graph. It's always, one of these really easy to make mistakes. Just take your time putting that into the calculator.
It's gonna take me a second.
Yep, take your time. It's you gotta be able to graph it and get the so you're gonna want to do like kind of y1 and then your y2 will be 60. Figure out where they, where they intersect.
Wait, so they intersect twice. You have to find both of them?
Yes.
So one of them is 1.866.
Good. Yep. That's correct.
Don't they intersect 3 times?
You're only going from 0 to 4.
Okay.
And that's the important thing is you cut off your graph or you just only get those two that are there. Because you're right, could go on forever.
And then the other one is 3.52.
Yes. Good. Okay, so you get those two values, and that's part I. That's the find the time interval. So somehow you'd want to indicate that the time, 1.866 less than or equal to t, less than or equal to 3.519, like that. The second part is to determine the total distance traveled by the particle during the interval when the velocity is at least 60 meters per hour, right? So the graph here is pretty important because what they're asking for is now the area under the curve from those two regions. So the second one is the integral 1.866 3.519, and you're integrating that function 45 square root t cosine 0.063 t squared dt, and your distance will be in meters. There's a small little thing to think about here. Since it's always positive, you don't have to worry about absolute value. But if there were a crossing, because it wants total distance, you would then do absolute value. But this one you just do as is.
I got 106.
Yeah, that sounds right. All right, so part D. At time t equals 0, particle Q is at position minus 90. Using the results from part B and the function VQ from part C, approximate the distance between particles P and Q at time t equals 2.8. All right, so there's two particles. There's P, which we've already kind of looked at. So in part B, we found that, and I don't know if I've got the number here. Part B. Oh yeah, can you give me this number again for part B?
40.75.
Okay, so 40.75. So particle P has gone 40.75, but Q is a different story altogether. Q is starting at minus 90. Okay, so there's this thing, which is there's Q of 0 plus the integral from 0 to whatever time unit that we're interested in. Okay, and then you're integrating that function 45 square root t cosine 0.063 t squared from 0 to 2.8. But this time you have to add in this minus 90 for the Q of 0. That's why they're giving you this. T equals 0, it's minus 90. All right, so we got to go back to the calculator one more time. I will also do this. We definitely need this one. Brutal. Lots of these calculations.
Okay, yeah, I got that too.
So we have to add these together. So that gets you to 45.938. And they just want the distance between here. So that means just how far apart are they? They don't care about direction. So it's 45.938 minus 40.75. And don't forget your units. Like above all else, they really do care about that. And I think you get like half a point for units. So even if you don't know how to do it, put the right units in with any answer, you'll get some credit, I think.
Wait, oh, where'd you get the 40 points? Oh, not from B. Okay.
Would be, yeah. It is rare that they actually do like, hey, go back to the previous part. Sometimes they do. All right, so on to page 2. All right, so the continuous function f is defined on the closed interval -6 to 5. Well, that's weird. Why aren't they giving you the rest of it? Okay, we'll see. See how they're not giving you anything left of -6? Don't really understand that, but okay. The figure above shows a portion of the graph. Okay, that's why. Consisting of 2 line segments and a quarter circle centered at the point 5,3. So that was good to kind of denote that. It is known that the point 3, 3 minus square root of 5 is on the graph of f. All right, well, maybe we'll use that later on. Put that in blue here. That's somewhere there. All right, if integral minus 6 to 5 f of x dx equals 7. Find the integral from minus 6 to minus 2. Okay, so we know that the entire area is 7, but we're interested in dx plus integral minus 2 to 5 f of x dx. All of this equals 7. And we're trying to find this one on the left here. To find this one on the left, if we knew the one on the right, we could then subtract. So what they're suggesting here is that you have to find the area under the curve for all of these regions. So I'm going to grab another snip of the graph so we can zoom in a bit more to talk about how to do that. Any questions though? I mean, this is just one of the integral rules where you can separate the integral into two pieces.
No, I got it.
Okay. All right. So the what I used to do is draw these shapes and then see if they canceled out. So the one up top here is positive, that one's negative, they cancel out. So there's nothing for that part because we're going from -2 all the way to 5. This one, not as good. You gotta sort of figure out what this is. It looks like it crosses at 0.5. So this does look like it cancels out with this here. And so you could just find the area of the red, which is a trapezoid or a trapezoid plus a triangle. You can start counting boxes, move this thing around. It ends up being 2. You just figure that out, that red area is 2. The last one's probably the most difficult. It's a composition of shapes. It's the box, the square here, take away the circle. So it's 9 minus the circle, which is a quarter circle, radius of 3. So pi 3 squared divided by 4. So 9 minus 9 pi over 4. Is that okay?
Yes.
Maybe. So here's what we've got. We know that the first one is 0, the second one is just 2, and the third one is this 9 minus 9 pi over 4. So we're going to put that in for these unknowns. So the integral from -6 to -2, f of x dx plus, I'll color code it here, 2 plus the 9 minus 9 pi over 4, that equals 7. So treat this like a variable on the left. You're just going to move some stuff around. This is 11. Subtract 11 from both sides. It's -4. Move the 9 pi over 4 over. So it ends up being 9 pi over 4 minus 4 is your -6 to -3.
Okay. That was a lot.
Yeah, there's a lot there. And if you're not comfortable with kind of like canceling out regions, there's even more work because you got to, oh, that's an area of 1/2 and that's -1/2 and that's 1/4 and +1/4. It just, the more you can do without writing down, the better, but it is kind of a lot here.
Wait, isn't it -2 integral on the integral, not -3?
Where,
On
oh
the
yeah,
very bottom?
yeah, it's a 2 there. Yep. All right, so for part B, really don't have enough time to do it. I'll just sort of talk about what to do. You want to break this apart into 2 times the integral from 3 to 5 f prime of x dx plus integral 3 to 5 4 dx. The one on the right just ends up being 4 times 5 minus 3. The one on the left here you get from doing the area under the curve. So from 3 to 5. Which is a bit more involved. It does go back to this point right here. You're gonna have to use that for part B.
Okay.
But we are unfortunately out of time. I know that
Thank you.
we didn't get through everything, but that's going to do it for us